Okay, so welcome again to a new lecture. This is lecture number 21 of phase equilibria. So we'll first recap the last lecture's content. So in the last lecture, we discussed about implementation of lever rule. In a binary phase diagram. So we considered a phase diagram like this. And in this diagram, we considered the formation of phases at various temperatures. And so basically we looked at how do composition of phases and their proportions change in a phase diagram. This is what we discussed. So we had alloy composition C0, and we looked at various temperatures T1, T2, T3, T4 and so on and so forth. It might not be in the same order, but roughly the trend that we looked at. And what we did was we basically looked at the composition. So this point, for example, has single phase region, its composition is C0. T2 point, at T2 you have two phases, liquid and solid. Liquid composition is given by this point, solid composition is given by this point. At T3, liquid and solid again are in equilibrium, but liquid composition now given by this point, solid composition is given by the point on the right. So, and at T4 you have again single phase solid whose composition is same as C0. So this would be say CS2, CL2, this would be CS3, this would be CL4, and the proportions would have varied according to the compositions. So the proportions of, for example, in this case percentage solid, weight percent solid would be, for instance, at T2 it would have been CS2 C0 minus CL2 divided by CS2 minus CL2 into 100. So this would be the weight percent of solid, and weight percent liquid would be 100 minus weight percent solid, which would be equal to CS2 minus C0 divided by CS2 minus CL2, and that is how you work out the composition and fraction of phase fractions of different phases in two phase equilibrium. Now let us move on with it and see what we want to achieve in this lecture. So in this lecture again, what we will do is that we will first look at the microstructure development in a binary phase diagram, and then we again get back to calculation of various phases and their fractions especially in a eutectic system, because that is what is most interesting, very interesting. So first look at the microstructure evolution, and the condition which we consider is that alloy is cooled slowly such that there are no composition gradients in each of the phases. So basically what we are going to talk about is how a equilibrium microstructure develops in a binary phase diagram. So first let us consider the case of let us say the example that we choose initially is a copper nickel binary system. So what we do first is we first make a diagram. So So this is a copper nickel phase diagram. Okay, in the copper nickel phase diagram, as all of us know, this is copper, this is nickel. Copper melting point is 1083 degrees centigrade, and nickel melting point is something like 1500 something. Let me just see how much is it. It's about just 1 second. It's about 1450 degrees centigrade roughly. It's not approximately, okay, or maybe nearly 1500 degrees centigrade. So the phase diagram is so let me just draw this a little further down. So let's say this is 1083 degrees centigrade. This is temperature, this is percentage nickel. So the phase diagram would have a behavior like that, and above this point you will have liquid plus solid, and then you will have liquid plus alpha, and then you will have alpha. So alpha is basically the solid solution of copper nickel. Okay, it's basically substitution solid solution because copper and nickel are soluble in each other. Now let us look at the evolution of phases. So let's first look at overall composition of about 35% nickel. So let's say we are at this point. So if I draw a vertical line at this point, so this is, let's say, so we say that C naught is equal to, so this is C naught, and C naught is 35 weight% nickel. Okay, so and we will look at the phase formation in such a manner so that we are at point A here, we are at point B here, we are at point C somewhere here, and then we are at point D, and then we are somewhere here point E, right. So that is how, so we will first look at what is the microstructure at point A. So we can see that at point A what you will have is, you will have 100% liquid. So you can draw the phase diagram, you can draw the microstructure. So if you look at the system of this composition, then you have liquid, 100% liquid of composition C is equal to C naught. Okay, so you have 100% liquid of composition C is equal to C naught. Now let's look at point B now. So this is what we also did in the last class. So if you look at point B will tell you, so this is at point A, point B will have some amount of alpha, very tiny amount of alpha forming here and there. So this is alpha, let's say, but remaining is all liquid. Okay, so this is newly formed alpha, and this is all liquid, and we can find out the composition of these two phases using tri-line rule and the phase fractions using lever rule, just like we did in the last class. If you look at point C will have this alpha would have grown and some more new alpha would have formed. So basically what you will have is, you will have bigger crystals of alpha, and the shape will depend upon various factors, but let's consider the shape will be irregular, just it would have grown roughly equally in all the directions, so sort of irregular shape. So this would be your microstructure at point C. This is alpha crystals which have grown bigger and some more have formed, and your liquid phase has decreased in fraction, as you can work out using lever rule. So you have liquid phase, okay, and the compositions etc. you can draw by drawing a tie line, which I have explained how to do it in the last class. And then we reach point D. So let's now look at point D. Point D is the point which is just above the solidus line. So at point D, if you look at the microstructure, what you will have is, you will have nearly everything is converted into alpha. So you have very large grains of alpha. So this is all alpha, which has grown very big. Let's say this is some more alpha here. So you have lot of alpha. So this is alpha, and of course you can determine the composition of this alpha using tie line, and then you have very little amount of liquid left here and there. So this is liquid. So you have very little amount of liquid. So amount of liquid progressively decreases as you decrease the temperature. The alpha grows in size. The composition of liquid becomes more and more rich in copper, less in nickel, and the composition of solid becomes more and composition of solid also, as compared to the first solid form, comes closer to C0, which is the equilibrium concentration. So this is, let's say, C alpha 1, this is C liquid 1, this is C alpha 2, this is C liquid 2, this is C alpha 3, and this is C liquid 3. So this alpha would be C alpha 1 and this would be C liquid 1. At this point, alpha would be C alpha 2 and liquid would be C liquid 2. At this point, it would be C alpha 3 and this would be C liquid 3. So liquid is getting smaller and smaller in proportion, and it's getting depleted in nickel gradually. The alpha also, as compared to the alpha which formed right at the beginning, has become depleted in nickel, but it's coming closer to C0. Okay, it's coming closer to the equilibrium concentration, because eventually when the whole solid forms, everything should be equal to C0. So you have alpha approaching, composition of alpha approaching C0, whereas composition of liquid is getting reduced to very less nickel, and eventually at point E, or even let's say at this point just below D, if you look at just below D, let's say just below D is the point which is E, and we call this as F. Okay, so at E, all of liquid would have changed into alpha. So what you will have is something like this. You would have, so these are grains of alpha which have merged into each other. Another grain of alpha which is merged into, which has grown bigger, and this is another grain of alpha which is grown. So this is all alpha. Okay, I can draw the grain boundary using another color. So you will have grain boundaries something like that. These are the different nuclei of alpha which have grown and impinged upon each other. So what you have at this point is 100% alpha of composition C0. So this is how the microstructure in a binary isomorphous system would grow. And you can determine the phase fractions and compositions using tie line and lever rules. Now let us look at the formation of alloy in a now what will happen when the alloy is, now in reality we are doing this experiment. So if you do this experiment, if you do it slowly enough, you will get what I have shown you here, but very rarely in practice the cooling is slow enough to give you a perfectly homogeneous alpha phase and perfectly homogeneous liquid phase. So what will happen there is, if I rub this point, what will happen there is, if you now make a phase diagram of imperfect cooling of a system, so this is copper, this is nickel, so this is Tm nickel, this is Tm copper, okay, and this is weight percent nickel. Now what will happen in reality is, if you now consider, let's say I have a composition, this composition C0. Now what will happen in reality is, you start cooling, when you come to, so you come from point A, and point A will have a microstructure which is 100% liquid of composition C0. Okay. When you come to this point, let's say first point, when you come to first point, at this point, which is point B, you have liquid of composition Cl1 forming and solid of composition C alpha 1. So this is liquid plus alpha, liquid and alpha. This is fine. So you have first solid forming of composition alpha prime. Let us say this is nearly I don't know, we are starting at 35%. So this is nearly let me see, let's say about 75%. Okay. Now what will happen at this point, if I look at the microstructure at B, you have tiny crystals of alpha formed. So this is, and the remaining is all liquid. So you have liquid of composition Cl1 and alpha of composition C alpha 1. Now what will happen is that when you go down to point, let's say this point now, point C, this is point C. At this point, ideally you should have all the solid of composition, this is C alpha double prime, and this should be the liquid of Cl double prime. But what happens in reality is that the first solid which had formed was this. Now the next solid which is going to form around this already formed nuclei is this layer, sorry, undo, okay. So the next solid will form around this. Okay. So what will happen now is, now ideally whole of this solid would have been of same composition, but in reality the diffusion or the movement, so basically overall composition should have been C alpha double prime. But what has happened is, the first alpha which formed was of composition C alpha prime. The next alpha which is formed is C alpha double prime, because C alpha prime was unable to redistribute the nickel atoms to the next forming solid because of lack of time, because movement of atoms in solids require times, because solids are diffusivity of solid, as you will see. As you will see from the fundamentals of diffusion, diffusion is nothing but movement of species, and movement of species or atoms or molecules in liquid phase is faster as compared to solid phase. In solid phase, the diffusion or movement of atoms is very fast. It could be quite fast at high temperature, but at relatively lower temperatures, it's lower than definitely in liquid. So what happens is that if this alpha which is formed earlier is unable to release its solute to the newly formed alpha at lower temperature, what will have? You will have compositional difference. So the inner alpha which is formed earlier will be of composition C alpha prime, and the outer alpha which is formed on the outer periphery will be of composition C alpha double prime. So this would be the outer alpha. Okay. When you come to now point D, let us say at point D, again the newly alpha formed is of composition C alpha triple 3 prime, and you have C alpha. So again at point D, what will happen is that within this microstructure, of course this alpha would have grown. So I am just drawing it very schematically. So this is the first alpha which formed at T1. Now don't worry about the sizes, these are just schematic diagrams. So this is alpha which is formed first, this is the alpha which was added to previously formed alpha at T2, and the next one which will form at T3 will be something like that. What you will now have is, you will have this of composition C alpha prime, this of composition C alpha double prime, and this of composition C alpha triple prime. So as you keep doing it, when you go to point 4, and this is because of a relatively slower solid state diffusion of atoms than in liquid state. So similar, you can argue that similar composition gradient can also exist in liquid, but liquid is the redistribution of solute is faster in liquid as compared to that in solid. As a result, the liquid is fairly homogeneous as compared to solid. Now when you come to next point, at this particular point, then the composition should have been C alpha 4 prime, and this is C liquid 4 prime. So when you come to point E, so point E I can draw here, let us say, if not there. So at point E you will have, so initial alpha, followed by the alpha which is formed at T2, followed by alpha which is formed at T3, followed by now the alpha that will form at T4. So this would be C alpha 4, and then you will have liquid. So remaining, so you will have liquid, in all of them, and the amount of liquid will reduce as you. So now when you come to this point, when the solidification is nearly complete, at this point your microstructure will be, so again, sorry, the blue one goes first. So the blue one blue one. So then comes the red one. And then comes the green one. Then comes the magenta one. And then comes the, let's say, the purple one, the final one. And so on and so forth. So you will have now the final one, C alpha, and this is liquid. So what you see is that now ideally you should have gone along this line. The overall whole solid would have been at C alpha prime, C alpha double prime, C alpha triple prime, C alpha 4 prime, and C alpha 5 prime. But in reality what has happened is that you have formed solid gradually, and the first formed solid has higher composition as compared to the last formed solid. As a result, the overall composition of the solid, so overall composition of alpha is greater than C alpha 5 prime. So the one which is formed here is of this composition. So ideally this last solid should have composition like this, but in reality you have composition starting from C alpha double prime ending at C alpha 5 prime. As a result, the overall composition would be the sort of average of this two. So the solid composition will now vary in this fashion. If you look at the solid composition will vary as this dotted line, because the overall composition of solid is higher. So solid composition will be shifted here, here, here. So this is now the overall composition, and as a result what happens is that in a binary phase diagram the solidus line is shifted downwards. As a result, you will still have some liquid left at this point. So the last liquid to solidify will not be at this temperature, the last liquid to solidify will be at this temperature, because the solid composition has changed. As a result, the liquid is also getting more and more depleted in solute, because the solid composition is more than what it should have been at equilibrium. So liquid has gotten depleted and this solidus has shifted further downwards. So because of this, the last liquid to freeze would be at this point. So you will have some solid and this will be the last liquid to freeze. So this is the extra degree of cooling that one needs to provide because of inhomogeneous compositions, because of non-uniform cooling, because the solidus line has shifted from here, from there to here. So this is the shift of solidus line that you will obtain, and as a result you will have liquid present in the microstructure not until this point, but until this point. So this produces a microstructure which is very inhomogeneous, and that is why one needs to carry out heat treatments, etc., to further homogenize the microstructures. So obviously at this point what you will obtain at this point is a microstructure which is basically microstructure with composition variances. So you will have rings of different contours of different compositions. I am now using different colors now. So this is how the composition will vary inside the solid. So these will be the contours of nickel concentrations or you can say this will be the concentration gradient, What we have done in this lecture is we have looked at the microstructure evolution in a binary system, copper nickel system under both equilibrium and non-equilibrium condition. We will further dwell on this in the next lecture before we study the solidification in a eutectic system. So, thank you very much.